so I got these 3 links. Please open them so that you can have them on your screen as well. And let me share my screen. Okay. Okay, so for the first run, we're going to go through some visualization just so you guys know the basics, what it actually means, what it actually is, and then we can go through some of the details in terms of implementation in the paper, which is here, and of course some mathematics. Then the third time we'll go through the code. So it'll be like a lot of, each layer will have, each time we'll have more details. Okay, so transformer is basically, in a nutshell, self-attention, and it's multi-headed, multiple self-attention with encoder and decoder structure. So that's, kind of a one-line statement on what it is. And we'll explain what multi-head self-attention is, and we'll explain how that combines with encoder and decoder structure. Cool. So, and it says right here, in this post, we'll look at the transformer, a model that uses attention to boost the speed with which these models can be trained. And that's one of the advantages of transformer. And we'll see the computation complexities in a little bit. And it's because of that that's parallelization and also the speed of computation that comes with it. You can then it's you can train models like BERT using just encoders of the transformer architecture, and also GPT using just the decoder parts of the transformer architecture. In Europe, then people can, like GPT-3, GPT-2, these are enormous models, and because of this computational complexity, like you can actually do that. Yes, it was proposed in the paper, attention is all you need. And but it's actually, it's probably self-attention is all you need, because it's the original. This is not the original attention paper. Original attention paper is, I think, was from 2014 by Benjail, I believe. So this is more so self-attention with encoder and decoder. So. Okay, so the high level look, basically we have the input of, I believe this is Portuguese, and then we have the transformer in the middle, and we output English. I am a student, and what's in that transformer is this encoder and decoder structure, and we'll explain a little bit in detail. And it's not just one encoder, it's not just one decoder, it's actually a bunch of encoders and decoders stacked against each other. Okay, so yes, the encoding component is a stack of encoders. The paper stacks 6 of them on top of each other, meaning whatever you output flows into the input of another encoder layer. And so there's nothing magical about the number 6. One can definitely experiment with other arrangements. So the decoding component is a stack of decoders with the same number. So we got 6 encoders stacking against each other, and we got 6 decoders stacking against each other. And the way how they interact with each other is the decoder would actually take some outputs of encoder and use that as part of decoder. And we will explain that in details in a little bit. So how are these encoder and decoder architected? The encoders are all identical in structure, yet they do not share weights, of course. Each one is broken down into 2 sublayers. Okay, so this is encoder architecture. Self-attention, which we mentioned. And on top of that, it's a feed-forward neural network. Of course, I think this is oversimplified, and we'll look at the entire architecture in a little bit. The encoder's inputs first flow through a self-attention layer, a layer that helps encoder look at words, other words in the input sentence as it encodes a specific word. We'll look at self-attention later in the post. The outputs of self-attention layer are fed to a feed-forward neural network. And feed-forward neural network is, simply just some linear transformation plus an activation function. I believe you do it 2 times here. So 2 linear transformation. The exact same feed-forward network is independently applied to each position. The decoder, okay, so let's look at the decoder a little bit. The decoder has both of these layers, right? So we got self-attention here, feed-forward here. And again, we'll talk about what self-attention is in just a little bit. So we got self-attention here, feed-forward here, and it's the same here, right? Feed-forward, self-attention, but adds another layer of encoder and decoder attention. That's where you take the outputs of encoder to decoder. So, and some outputs, not all the outputs. It will be incorporated into this layer. Okay. The decoder has both of these layers, but between them is an attention layer, which is this layer, right? That helps the decoder focus on relevant parts of the input sentence, similar to what attention does in sequence-to-sequence models. Okay, I want to pause here. This is very high level. Anyone has any questions before we move forward?
Yeah, do we need the same number of decoders as you have encoders?
That's a good question. I don't believe so. I think it says there's nothing magical about that. But I guess, I don't think so. But anyone else has a different opinion?
I have a different question. In your diagram, you've shown that all the input goes through all the encoders at first, and then it goes to the various decoders. Is it possible to go from the first encoder to the first decoder, and then also from the second encoder to the second decoder, and so on?
I don't believe that's how it's structured. So if you look at
yeah, so for example, here
so
it shows.
Actually, yes.
Okay.
So yes. I probably misspoke. It seems like this directly flows to that. And
okay, so that introduces a lot of flexibility into what you can do.
Yeah, because I was thinking about this. Because on this graph, like encoder 1, encoder 2, and you see this goes to decoder 1 and decoder 2. So I don't know why this was not consistent, but that's a good question. Perhaps, when we go through this, we'll have better thoughts on that. Anyone else has thoughts on this?
Yeah, so I think each encoder is nothing but a layer. And then as we go, like you have a different layer is capturing a different representation of the word or a sentence, and all of them are going parallel. And in the end, what's going to happen is I think the information from different encoders, that is, i.e., different layers, get together to have some representation or the combined representation. And that's why I think he has the last layer going into a decoder, where it collects all the information from all the encoders, and then it's finally that's the complete representation. And I think that's my understanding. I could be wrong.
Yeah, so I don't know. That was my understanding as well. Like it only takes the output from the last layer of encoder.
And that's where parallelism comes into a picture, that it doesn't, when we feed in the whole sentence, it doesn't go sequence-wise sequence. It goes just as a whole in like 8 layers or whatever, like number of encoders. But ultimately, I guess, end of the day, it has to collate the information from all the encoders and pass on to decoder as there is a pointer in the for the decoder. That's my understanding, right? At least.
Yeah, that's what I thought as well. Otherwise, I mean, the previous question is does it have to be the same number of encoders and decoders? If this is the case, then they would have to be the same, I guess. But I don't think so. Okay, we'll keep this question in mind and keep going. Okay, bringing the tensors into the picture. So we'll do some vector or matrix multiplication in a little bit. And so each word is embedded into a vector of size 512. Will represent those vectors with these simple boxes. And so even though this is 4 box, but it's really 512. So this is 1 by 512, 1 by 512. The embedding only happens in the bottommost encoder. So it doesn't happen, I guess, every encoder. And the abstraction that's common to all the encoders is that they receive a list of vectors, each with the size of 512. In the bottom encoder, that would be the word embeddings. But in other encoders will be the output of the encoder that's directly below. Right. So on the second encoder layer, third encoder layer, they would just take, the output of encoder from the output of the previous encoder, basically. The size of the list is hyperparameter we can set. Basically, it will be the length of the longest sentence in our training data set. So we set it to, and I believe the paper sets it to 512 as well. And this is the dimension D model. We'll see that notation very often. So just remember, this is D model, dimension of the model. But it also would be is the length of the longest sequence in our training data set. Longest sentence. After embedding of the words in our input sequence, each of them flows through each of the 2 layers of the encoder, right? So we got 2 layers, self-attention and feed-forward for the encoder. Okay. We'll talk about how this is calculated in a little bit. Here we begin to see one key property of the transformer, which is the word in each position flows through its own path in the encoder. There are dependencies between these paths in the self-attention layer. The feed-forward layer does not have those dependencies. However, and thus, the various paths can be executed in parallel while flowing through the feed-forward layer. Okay. Now we're encoding. Okay. as we've mentioned already, an encoder receives a list of vectors as input. That would just mean, you know, if we have like, you know, bunch of words, then it would just be, you know, a list of these bunch of vectors. It processes this list by passing these vectors into a self-attention layer, then into a feed-forward neural network, as we said, then sends out the output upwards to the next encoder. So yes, so again, this when we output this, it flows into the next encoder, and there's 6 of them, right? The word age position passes through a self-attention process, then they each pass through a feed-forward neural network, the exact same network with each vector flowing through it separately. Okay, so now we're going to explain what self-attention is, because we already know feed-forward neural network, obviously. We just need to get to know what self-attention is. So say the following sentence is an input sentence we want to translate. The animal didn't cross the street because it was too tired. What does it right here in the sentence refer to? Well, the animal didn't cross the street because it was too tired. So it refers to the animal, right? But how do we let machine know that? Is it referring to the street or to the animal? That's a simple question to a human, but not as simple to an algorithm or a machine. When the model is processing the word it, self-attention allows it to associate it with animal. As the model processes each word, self-attention allows it to look at other positions in the input sequence for clues. What does it mean? Look at this graph. It connects, you know, it could be associated with all these words, right, in that sentence. But in the end, we want it to be associated with the animal the most. And look at all these lines. And these lines actually just means, so remember I said multi-headed attention? And so within each self-attention layer, there's actually different heads of attention. And I will explain what that means, like what that multi-head means. But right now, each head is represented by a line. And you can see here, these 2 lines are actually, or I guess, how do you say, like, it's represented the most, and it is the animal. So the model seems to be able to get it right, even though it still has some association with the other words. Okay. If you're familiar with the RNNs, think of how maintaining a hidden state allows an RNN to incorporate its representation of previous words vectors it has processes with the current one it's processing. Self-attention is a method of transformer it uses to bake the understanding of other relevant words into the one we're currently processing. So it's, you know, baking the understanding of other relevant words, meaning it to the animal, right? And also, you know, perhaps T didn't. Okay, and this kind of graph visualization comes from this notebook, and I'm gonna share that as well, just so you have it, but we're not gonna go through this. Okay, I just sent that in the chat. Now we're going to go through it in a little more details in terms of like how self-attention is calculated in a visualized way. And we'll go through some mathematics after that when we go through we'll go through that. Okay, so the first step in calculating self-attention is to create 3 vectors. Okay, 3 vectors. Okay, Q, and it's called QKV. These are the 3 vectors. From each of the encoder's input vectors, these are the input vectors. Okay, in this case, it's the embedding of each word. I don't know which exact embedding that they use, but you could think of this as word embedding, sorry, word to vec or word piece. So for each word, we create a query vector, which is this Q1 or Q2. And right, so for thinking, we have a, you know, as a word, we have Q1. For machines, we have Q2 as another word. So each word seems to have its own query vector, its own key vector, its own value vector. Okay. And obviously Q just relates to queries, and K relates to key, and V relates to value. And how are they calculated? They're calculated by using X1 or X2 to multiply with an embedding, a word embedding right here. And those are weights to be trained. And when you, this is 1/4, right? This is 4/3, and that's why you have a 1/3 here. And again, 1/4, 4/3, 1/3, same thing, 1/4 times 4/3, you got 1/3. So we're doing some vector to matrix multiplication, but in the end, this is not a vector. This should be a matrix. We're just, you know, using vector as an example. And we'll go through the matrix example like this in a little bit, but you get the idea. So, okay, these vectors are created by multiplying embedding by 3 matrices, these 3 matrices, right? That we train during the training process. Again, these are weights to be trained. And when you multiply these together, you get the QKV vectors. Notice that these vectors are smaller in dimension than the embedding vector. Okay, embedding vector is 512, remember? Their dimensionality is 64, while the embedding encoder inputs, output vectors have dimensionality of 512. They don't have to be smaller. This is an architecture choice to make the computation multi-headed attention mostly constant. So we get a glimpse of what multi-head attention means. It's just separating them out, splitting them out, and we're just cutting them out, right? Like in this case, we're cutting them into 8 pieces. And so it would have been 512, and we're just dividing by 8, and we get 64. And that's all it is. Okay. So yes, so this just explain this again. And so what are the query key and value vectors? So we're going to explain what these 3 vectors even mean. They're abstractions that are useful for calculating and thinking about attention. Once you proceed with reading how attention is calculated below, you know how much all you need to know about the role each of these vectors plays. The second step in calculating self-attention is to calculate a score. Say we are calculating self-attention for the first word in this example of thinking. We need to score each word of the input sentence against this word. The score determines how much focus to place on other parts of the input sentence as we encode a word at a certain position. Now, that's a lot to unpack. It's probably best to be visualized. in terms of how this is actually calculated. But I want to stop here to answer any questions if you have any, before we go into the details of calculation. Is everyone good? Okay. All right. Cool. So the score is calculated by taking the dot product of the query vector with the key vector of the represented respective words we're scoring. So we're literally just taking the dot product of Q1 and K1, and obviously the results of a dot product operation is a scalar. And notice that we are not dot producting Q2 and K2. We're just dot producting Q1 and K2. And for the third word, we're going to be Q1 times K, dot product K3 and Q1 dot product K4. And we're going to have a bunch of dot products of Q1 dot producting all the other words, key vector. Okay, so this is actually what it means when we say, hey, you know, how is thinking related to all the other words? Well, we're just dot producting thinking's query vector and with all the other words, key vectors. And that's how perhaps I guess, you know, the relation comes in when it comes to how one word is related to the other words mathematically. Okay, so if we're processing the self-attention for the word in position number 1, the first score will be the dot product of Q1 and K1. Again, right here, 112, that's the result. The second score will be the dot product of Q1 and K2, 96 as the result. Okay, and the third and fourth step are to divide the score by 8. The square root of the dimension of the key vectors used in the paper, 64.
Hey, Wenchang, so
Yeah.
can you remind me again, you know, so you do these dot products of Q1 and K1 and so on. Is bigger, what's the significance of a bigger value? And then can you remind me again, what's the reason why we dot product? I'm sure we discussed this many weeks ago, but I've forgotten.
Dot product can be just calculating, well, in this case, it's just a score. And you're going to divide that, and you're going to, you see this?
Yep.
112 actually gets scaled to like softmax of 88%, 0.88. So that's what it actually comes to. And dot product in the end is similarity, right? So if these two vectors are more similar to each other, and they're going to have higher softmax probability. And if they're not very much similar to each other, they're going to have a very low softmax probability. And we use dot products in many other algorithms and such as word2vec to kind of see how similar two vectors are to each other.
Cool, thank you.
Sure. Okay, the third and fourth steps are to divide the score by 8. Okay, we talked about that. This leads to having more stable gradients. So this is this, you know, we actually going to talk about this term scale dot product attention. And this is the dot product, Q and K, right? We just did that. And this is the scaling factor. We're scaling this by square root of key vectors dimension. Okay, so we are divided by 8. In this case 8, and which is square root of 64. So 112 divided by 8, that's 14. 96 divided by 8, that's 12.
What's
Then
the
we
D
apply.
in this case?
Yeah.
What's the D by DK.
DK is this dimension of the key vector. This K. Dimension of this, and it's 64.
So that would be 64. We started with 512.
512. And we have to, because of multi-headed intention, we're splitting that.
Okay, so
Yeah.
K we have learned by multiplying x1 with the WK, and then K1. So the weight number of columns in a weight was 64. That's why we have 64 in here. Is that correct?
Yes. So that's right. Yes. But if you, this could be six. This is like the column is 64.
Okay.
Yeah. But notice it says 512 here, and because we have multi-headed attention, and if we have 8 heads, this is actually 64, I believe. 64 columns.
64 columns. That's correct. Yeah.
Yeah, and hence this would have 64 columns as
64.
well.
Yeah. 64
Yeah.
dimensions, he is saying. And so any particular reason why we have weights of 64 dimensions whatsoever? We could have picked any 128, any number randomly, you know?
Well, this comes from, I'm pretty sure this comes from like 512 divided by, like it depends on how many heads you want to have. Yeah, so I don't think it's a random number you can set. Depends on how many heads you have. And but like 512 is the hyperparameter you can set, and you got to divide 512 with the number of heads. In this case, I believe it's 8 heads per self attention. Yeah, per self attention.
Yeah, it makes sense.
Yeah. So you don't actually, so it's 512 divided by 8. That's 64. And then we take a square root of that, that's 8. And we just divide it by 8 right here.
Yeah.
Okay, great. So, and we just softmax it, right? And softmax basically just normalizing that with the exponentiation function and get the probability that adds up to 1. In this case, we only have 2 words. That's why 0.AA plus 0.12 is equal to 1. And we're just literally softmaxing across 2 numbers. Right, so, but obviously in real cases, you have more than 2 words. Okay. And softmax comes in here, right? That's the equation. We'll talk.
Sorry, Wencheng, another question, please. Can you remind me how we came to 8 heads?
Square root of 64. 8 heads. Okay, I'm sorry. 8 heads. I think that's another parameter you can. That's another parameter. Let me see if the paper mentions about how many heads. Why they chose 8 heads. The paper is right here.
I think 8 heads is just a hyperparameter, right?
Right here. In this work, we employ H equals to 8 parallel attention layers or heads. And for each of these, we use DK, right? Dimension of key vector, dimension of value vector, equals to 512, right? D model, remember D model is 512 divided by 8, that's 64. And 64 also equals to dk and dv. So that's just, yes, I agree. They just employ 8, and so that's a hyperparameter. But you got to make sure 512 can be divided by 8, right? And it could be another number that could be divided, that 512 can be divided by.
I think maybe idea was that different heads learn different relations in the sentence, and
Yes.
8 sounds like enough, like he was in the lecture he was saying it's who was doing the action, the action, and to whom it's applied. That's 3 relations.
Mm-hmm.
And there are probably more.
Yeah. So that's the reason why we want multiple heads. We want 8 heads or some other number of heads. It's to learn different representation subspaces at different positions. So it's not, single attention is not enough to learn all the relationships that's presented here, right? Like ideally, you want to learn how it is related to different words, and that is done by different heads and different representations, different vectors or matrices. Basically, just you're just let's say you have, for word to vec, you have just one vector for one word, right? But what if this word has different context in a different sentence, and you actually want multiple heads, multiple vectors, multiple matrices to represent that? That's all it is. Any other questions? Is that clear?
It is, thank you.
Okay, great, thanks. The softmax score determines how much each word will be expressed at this position. Clearly, the word at this position will have the highest softmax score, but sometimes it's useful to attend to another word that is relevant to the current word. The 5th step is to multiply each value vector by the softmax score in preparation to sum them up. The intuition here is to keep intact the values of the words we want to focus on and drawn out irrelevant words by multiplying them by tiny numbers like 0.001, for example. The 6th step is to sum. Okay, so let's just softmax times the value. Okay, so when we softmax that and we times the value vector, right? So each value vector, okay? Each value vector, and again, value vector is this one, okay? We use, so we only dot product these these both Q and K vectors, right? We didn't use V1, and now we're gonna use this value vector to times this probability score. Okay, and we're gonna sum them up. Okay, so V1, V2, V3, V2 all the way to N, and we sum them up and we get a Z1. And that's how you calculate Z1 for thinking, just one word, okay? And Z2, you do it all over again, right? All the previous steps. So this concludes the self-attention calculation. The resulting vector is 1. We can send along to the feed-forward neural network. in the actual implementation, however, this calculation is done in matrix for faster processing. So let's look at how that. Okay, so I want to just recap what we've done because it's a lot, and just so everyone understands. Again, we got 3 vectors, right? Queries, keys, value vector, and it's represented by QKV. How they're calculated? They're calculated by X1 times WQ, this weight matrix that's trained, okay? X1 times WQ, you get Q1, X2 times WQ, you get Q2, and that's how you calculate a bunch of QKV vectors for each word. Okay, and how do we use them? What do we use them for? We dot product QK, okay, and we Q1 K1, Q1 K2, and Q1 K3, Q1 K4, and then we get a bunch of numbers, scalars, divided by 8, which is square root of your key vector's dimension, which is 8. Again, bunch of scalars, softmax stat, normalized to 1, times the value vectors, okay, bunch of value vectors, times the softmax score, sum them up to Z1, okay? That's how you calculate self-attention. I hope that was clear. Okay, so now we're gonna do a matrix version of it, not just a vector. So the first step is to calculate the QKV again. Now this time it's 2 by 4 instead of 1 by 4. But it's the same thing, right? 2 by 4, 4 by 3, and you get 2 by 3. You eliminate the middle dimension 4, right? So when you do matrix multiplication, 2 by 4 times 4 by 3, again 2 by 3, again 2 by 3. And finally, since we're dealing with matrices, we can condense steps 2 through 6 in one formula to calculate outputs of the self-attention layer. So this is exactly the formula we are seeing here in the scale dot product attention. And that just scale dot product attention is self-attention. Okay, that's what it is. Now we're saying dot product, but in the end, is it really dot product? It's really matrix multiplication, right? Yes, and it's scaled by this factor. In this case, it's 8. And you do that, you do softmax first, and then you matrix multiplication, do matmul again with V, you get your Z, okay? Again, any questions, any comments before we move to multi-headed attention? Okay, so I mean, it's a
just one question.
Yeah.
So if you just scroll a little bit before we are converting Q into Z, we are converting X into Z. Is Z the observed output?
Z is the output. You see the equal sign. So you do these calculations, then you get Z. Yes.
But my question is that how does it calculate these weights Q, KT, and V? Because if these weights have to be calculated, then the input and output both must be known, right?
Well, these are trained, and this is inputs.
Yeah, X is the inputs, and then.
And this is a train. This is, I don't know how they're initialized, but they're initialized either randomly or some different ways, and then you train them right through backpropagation and optimization. Yeah, and but you times these two together and you get this. And so when you get these and you feed that into this equation and you get Z output.
Okay.
Yeah.
But Z itself is not the final product or final output, because Z will be fed into some other things.
Yes, it will be fed. It will be concatenated together as because there are multiple attention heads, and you don't even, this is like people like to name it in a fancy way, but like attention copy or attention split. Just think about it as a bunch of splits, right?
Yeah.
And when you concatenate them together, you multiply with a weight matrix like this. Then you get your eventual Z, and then you feed it into
The next layer.
Yeah, next layer.
Okay. Okay. Thanks.
And back to this, right? So when we finish this, right, we have a bunch of Z. We feed that into a feed-forward neural network, and then we feed that into a second encoder. Then we do this again. Yeah. Someone has something to say? Okay. Any other questions, comments?
Yeah, I have a question. So if you can go back to the high level diagram where we had the self-attention and the feed forward, please.
Yeah, right here.
Yeah, so what's happening is in the self-attention, we have gradient descent because that's how we're getting the weights, right, calculated. But the feed forwards, there's no backward, there is no gradient, there is nothing of gradient descent, right?
That's a good question. I don't know. I don't know the answer. Whether this part is
feed
background.
forward as well, right?
Say that again.
There are weights in feed forward as well.
But it's not going back though, right? It's not true.
So there is a loss that happens at the end, right? A loss is calculated at the final step, like when you translate English into French or whatever, and then you have a loss at the end.
Yeah.
The whole thing, I mean, and then it back propagates all the way from there, and all the weights in your self-attention as well as your weights in the feed forward get updated.
Okay, my understanding was there was no back propagation in feed forward, but I might be wrong there.
There is.
Okay, I guess John was saying, like, since it's called feed forwards, there's probably no back propagation. I don't know. We might go through some codes that will implement this today or next session, but like we'll see, whether this actually gets back propagated. Stats.
So what exactly the feed forward is doing in this case?
We'll probably, let me see if the paper mentions it. I just know, I mean, you can just add. So in addition to attention,
concatenated pieces and shove them in as as pieces into the feed-forward layer. So the different pieces that come from self-attention are concatenated and thrown into a feed-forward network.
So we have 8 layers. So are we going to have 8 feed forwards, or is just one feed forward for the 8 layers where it combine the result together?
Each encoder will have one self-attention and one feed forward, and second encoder will have another self-attention and another feed forward neural network. So each encoder layer will have both of these.
Okay, so can you repeat again, Srinivas? You were saying it will combine the results. What do you mean combine?
You'll see what happens as when Cheng goes through the rest of the details of how it comes together. Different, like exactly what he has right now, Z0 to Z7. And you'll see what happens and how they're combined to put to the feed-forward network. Just as he goes through the next level of detail, because we're just at a particular step of generating self-attention, and then they're all concatenated, as you'll see in a minute.
So at this stage, I take that feed forward is nothing but this concatenation of the result from the.
No, feed forward is like, just to recall, feed forward is like your traditional fully connected network,
right
which is basically multiplying, and that's why what Gautam was saying earlier too, right? There is backprop through feed. A feed forward is just a fully connected network with a bunch of weights, and then an activation like ReLU or something like that following
It's
that.
right here.
Okay.
It's right here, Dinesh. So it's XW1 plus B, and this is just ReLU, right? Max 0, and that's, and then you do times W2 plus B2 again. That's just what it means by feed forward neural network right here.
It's basically once we get the attention gets trained further with the weights and devices, apply the activation, and then we have a final result afterwards.
Yeah. Then you feed that into, so you feed this result into another encoder layer.
Correct. Okay.
Yeah. Okay.
Thanks.
Great. Okay. So beast with many heads, and that is multi-headed attention. So this improves the performance of the attention layer in two ways. So why do we need multiple heads? So because it improves the performance in two reasons. Expands the model's ability to focus on different positions, right? So yes, in the example above, Z1 contains a little bit of every other encoding because we're doing dot products. Remember Q1 dot product K1, Q1 dot product K2. So even though we are doing that, it could be dominated by the actual word itself, right? Obviously, you are most similar to yourself. It would be useful if we're translating a sentence like, the animal didn't cross the street because it was too tired. We want to know which word it refers to. So since it refers to the animal, we want to know that. So it gives you more focus. It gives you the ability to focus on different positions. And instead of being dominated by the actual word itself. Second reason, it gives the attention layer multiple representation subspaces, right? Because you're splitting this to attention head 0, attention head 1, attention head all the way to 7, and that's 8 attention heads or 8 attention splits. You're splitting your attention intuitively with different matrices and hence different representation subspaces. As we will see next, with multiple head attention, we have not only one, but multiple sets of query key value weight matrices. The transformer uses 8 attention heads, so we end up with 8 sets of each encoder decoder. Each of these sets is randomly initialized. So I guess these weight matrices are randomly initialized. I was just assuming, but it actually says right here. Then after training, each set is used to project input embeddings into a different representation subspaces. And so these are initialized randomly, and you're just like times that, right? Again, we're just doing some matrix multiplications. But instead of doing 1 time, we're doing 8 times. And instead of, having a matrix with 512 as the number of columns, we're going to have 512 divided by 8, and that's 64, right? So now we have 64 columns. And again, 64 columns. And 64 columns, right? So right here. So that's that. And in the end, we're going to concatenate them together, right? Since we split them. And here you go. So if we do the same self-attention calculation we outlined above, just 8 different times with different weight matrices, we end up with 8 different Z matrices, right? Because we split our attention, our dimension a model 8 times, and divided by 8, that's 64 each. But in the end, we want to concatenate them together so that we don't change the ultimate dimension. This leaves us a bit of challenge. The feed-forward layer is not expecting 8 matrices, expecting a single matrix, a vector for each word. So we need a way to condense these 8 down into one single matrix. How do we do that? We just concatenate them. Then multiply them with the additional weights matrix WO. So we'll literally just concatenate them, not summation, not other stuff, just concatenate them, okay? The results will be the matrix that, multiplying that with a weight matrix WO that was trained jointly with the model. And then results will be Z matrix that captures information from all the attention heads. We can send this forward to the FFNN, the feed-forward neural network. So that concludes the self-attention calculation in a matrix format. Okay, and we're going to do another recap because it's a lot of stuff. First step, input sequence, input sentence, X. Embed each word with the word embedding. Split that into 8 heads. We multiply X or R with 8 matrices. And again, I believe X is also split 8 times. Calculate attention using the result QKV matrices. So we times that, right? We times X0 with W0, X1 was W1, X2 to W2, all the way to X7 to W7. And you get sort of 8 sets of QKV vectors. And you will get 8 sets of, right? 8 sets of Z matrices, and you concatenate them together, right? And you multiply, matrix multiply with WO to produce the output of the layer. I don't, somehow he didn't really say this is X0, X1, X all the way to X7, but I do believe this is also split. Correct me if I'm wrong.
I don't think X is split because you want your attention to be able to attend to all the words, right? So you would not split X. So each attention head would get the entire X so that it's able to attend to all the words.
Right, but all the words are here, right? So if I'm just splitting through the columns and thinking machine and all the words are still here, I'm just splitting by columns.
Okay, by columns. Yeah, I'm not sure about that. Could be.
Okay, we'll go through the implementation. I believe it's somewhere here. I believe this is the splitting function, splitting heads. We'll go through that. Maybe I'm wrong, but this function, we'll go through that later on. But that's how it's implemented.
Did you say again, why do you think X need to be split?
I'm just thinking about the, I mean, does the shape actually make sense when it comes to matrix multiplication?
Yeah, but yeah, so you're gonna have X is just the one word, the embedding for a first word, isn't that correct? And then you're gonna have an X1 is the embedding for a second word. So Oh, I get it. What you're saying. Yeah, yeah. I think I got what you're saying. Yeah, because
Yeah.
you have W0Q, W0K, W0V. So you want to see the X into 3 parts.
Yeah.
No, actually, why would you see? Because you see the W, you have the W's are Q, K, and V. These are the 3 different metrics, weight metrics we're going to have.
Mm-hmm.
And then they will drive Q, K, and V from a same embedding as X. Because the W, W, Q, K, and V are going to get learned from the X. It's the same embedding which get fed, which is going to turn into Q, K, and V via the W, Q, K, and V. But it says embedding is same as X, because you wouldn't have a 3 different embedding for X. You know what I mean?
I understand it's not 3 different. I'm just splitting them, and in the end, everything is going to be concatenated together.
Yeah, but then my point is,
you see this reshape? So
yeah.
X is being reshaped here, splitting the last dimension into number of heads depth. So we'll go through that because it's being reshaped here, and I could be wrong. I'm just saying it seems like this is how it's implemented. And the depth is 64, right? Dimension mod of 512 divided by number of heads 8, and that's 64. So you have 64, 8, and batch size, and you have your X. Right, so it's X, batch size, 8, and 64. It's not 512 anymore. I could be wrong. Again, like let's go through that. Let's just hold that towards later when we go through this.
Mm-hmm.
Okay, because I'm literally looking at the Google's own. I mean, this is Google's paper, right? Transformer, and I'm looking at Google's implementation. So this is not a random implementation from somewhere else. This is the implementation. So yeah, and we'll see. Okay, let's keep going for the sake of time. Okay, other than that, is everything clear? Does anyone have any other questions?
Maybe you'll be explaining this at a later stage. What's the difference between query key and value? Or did you already explain it?
So key and value vectors are fed to the decoders.
Yes.
And query vector is not. So
Okay.
in the encoder structure, K and V are fed to the decoders, but Q is not. That's the biggest difference.
Okay.
But in terms of how they're calculated, it's just matrix multiplication, and they're just trained differently. Yeah.
Okay.
Sorry, could you just also provide the link for the Transformer Practice Collab notebook in the
Yeah,
chat?
I did. I provided 4 links. The third link is the.
All right. Okay, great. Thank you.
Yeah, sure. Okay, so let's keep going. Now that we have touched upon attention heads, let's revisit our example from before to see where the different attention heads are focusing as we encode the word "it" in our example sentence. So as we encode the word "it," one attention head is focusing most on the animal. So this attention head, right, is focusing most on the animal. So I guess I was wrong. Not every line is a head. Every color is a head. Correct myself. every color is a head. So green is a head. This this orange or brown color is a head, and this one is, look at this. This is focusing more on the animal, and this is focusing more on tired. And the way how this is tokenized, it's subword tokenization. So it's actually not just word tokenization. And we'll see that in a little bit in the implementation code. While another is focusing on tired, right? Tired, right here. In a sense, the model's representation of the word it bakes in some of the representation of both animal and tired. So that's that. If we add all the attention heads to the picture, so again, 8 attention heads, right? 1, 2, 3, 4, 6, 7, 8, 5, 6, 7, 8, and these are the 8 colors. However, things can be harder to interpret. Yes, you know, if we look at a bunch of colors, it's just harder to explain. But you know, it was easier here. Representing the order of the sequence using position encoding. So we're not just using X. That was a bit simplified. We are also adding a position encoding. How is it calculated? How is it implemented? How's it implemented? We will do that here, okay? And we'll explain that in the paper as well, but it's implemented here. Okay, and it's calculated like that. So, and it's literally summation. I have no idea why summation works. I've always thought, you know, if you're just adding them together, how does that work? Coming from not a mathematical background, it's harder for me to understand why things can be just summed together and still work. Anyone has any ideas? Because I mean, I've always thought, you know, for a lot of these things, concatenation would work, obviously, because you're not, you know, summing numbers together, you're just concatenating them, you're keeping every number. But summing up is a little confusing to me.
Why do you think it wouldn't work?
Because I was just thinking, you know, I mean, in a sense, let's say every vector would have its own meaning. And if you add 2 vectors together, wouldn't that dilute the meaning or confuse the 2 meaning from 2 vectors? I mean, is summation actually like, you know, including all the meaning from 2 vectors?
I mean, the function is still intact. Like when you do backprop, the gradient will still flow separately to your positional embedding and to your actual embedding.
Okay, so they're not.
Yeah, it's still there. I mean, even though you add them, the function that you implement is still intact. So yeah, gradients can still flow.
Good point. Good point.
And you are inputting words, right? So when you just concatenate them, you are inputting first 4 words and then you are inputting positions. So it wouldn't make sense, right? As opposed to adding them.
Yeah, that's a good point. Cool. Okay, let's keep reading. So the reason why we want to add position encoding is that it's the sequence or the order of the words in a input sequence is missing. So we need to add the position of each word in the input sequence or sentence into the embedding. To address this, the transformer adds a vector to each input embedding. These vectors follow a specific pattern that model learns, which helps it determine the position of each word. or the distance between different words in the sequence. The intuition here is that adding these values to the embedding provides meaningful distances between embedding vectors once they're projected into QKV vectors during dot product attention. Okay. So once you add them together, then you can call this embedding with time signal, or sequence signal, or position signal. If we assume the embedding has a dimensionality of 4, the actual position encoding would look like this. Okay. So this could be learned as well, this position encoding. It's not just 1, 0, 1, 2, 3, 4 as index. It's not just index. This can be learned. And what might this pattern look like? In the following picture, each row corresponds to the position encoding of a vector. Each row is a position encoding of a vector. So the first row will be the vector we would add to the embedding of the first word in the input sequence. Each row contains 512 values because each input sequence has 512 dimensions, right? And that's why each row would have 512 values to be added on top of the embedding. Each with a value between 1 and -1, we've color coded them so the pattern is visible. Okay, so a real example of position encoding for 20 words with an embedding size of 512, so 20 words, so 20 rows, embedding size of 512, again 512 columns. You can see that it appears split in half down the center. That's because the value of the left half are generated by one function which uses sine, and the right half is generated by another function which uses cosine. They're then concatenated to form each of the position encoding vectors. Again, it goes back to this sine cosine calculation. So from 0 to 215, that's how it's calculated. From 216 to 512, that's how it's calculated. The formula for encoding is described in the paper, which I just showed you. You can see the code for generating position encoding. This is not the only possible method for position encoding. However, it gives the advantage of being able to scale to unseen lengths of sequences. So there is an update. I don't think we need to go through this. The residuals.
Wenchang, could you go back to the rationale behind the sines and the cosines that will help you to determine the time sequence? Because that's not it's not very intuitive.
I have no idea. Someone else says the answer.
Okay, so I mean,
I think the
What-
positional encoding generates a unique number that for each position that sort of allows that when you add it to the vector x, it now actually encodes a piece of information in each position of the vector that tells you where it is in the sentence. That's what it's designed to do. It's designed to keep track of the positions of each word.
So it has to do with the sinusoids. Okay,
Yeah, I mean, I'm okay with the sine and cosine. I mean, I know what those are. It's just if there was an intuition behind why we would suddenly use them versus, yeah.
Um,
Yeah,
Go ahead.
one advantage of using sine is that it's periodic, so you can't hit a limit. If you used a linear timing sequence, you'd have to fix some kind of physical limit. But in this case, you can, even if it hits the physical limit, it will still continue generating values.
So it says right here, the wavelengths, right? This is actually a wavelength function. The wavelengths form a geometric progression from 2 pi to 10,000 times 2 pi. We close this function because we hypothesized, we chose this function because we hypothesized that it will allow the model to easily learn to attend by relative position, since for any fixed offset k, PE position plus k can be represented as a linear function of PE pos. I had a hard time understanding what this means, but it seems like it provides a geometrical progression. And I think that, I guess that corresponds to what the previous person was saying.
I think at a high level, you can just imagine, without trying to understand the details of what this is that it's trying to add something at each position to add a unique value that in the future represents, that helps you to understand which word that was in the sentence, you know, which the location of the word in the sentence. So you should think of it as a black box that adds something at each position that uniquely allows you to sort of figure out in retrospect where that word was in the sentence.
Yeah, so I would look into the sinusoid function. Okay, it seems like that's what they use. They just chose that function, and there are a bunch of, you know, that's what you do as a research scientist, I guess. You got to choose functions that work. And they also experimented this with learned position embedding, right? And found that the two versions produced nearly identical results, but they chose that because it allows the model to extrapolate to sequence lengths longer than the ones encountered during training. So they chose this because of these reasons. But
Okay, it's all right. Thanks, Wencheng. I appreciate that. Yep.
Yeah, sure. But yeah, again, like without a deep background in mathematics, it's just hard to explain these things a lot of times. Cool. So let's keep going. The residuals. One detail in the architecture of the encoder that we need to mention before moving on is that each sublayer in each encoder, again, this is a sublayer, this is a sublayer, and this is one encoder. Okay, and position encoding is added here, right? This is your word embedding, this is position encoding. You add some of them together, feed that into self-attention, do add a normalized layer normalization, and feed that into a feed forward, another layer normalization. Then you feed that into a second encoder. This is a more complete picture of encoder architecture than this one. So this was a bit simplified. Now, obviously, you know, we would need to always normalize your operations either with layer normalization or instance normalization or like batch normalization, you know, different kinds of normalization techniques. So yes, layer normalization. We'll talk a little bit about that when we try to implement that. So if we are to visualize the vectors and the layer norm operation associated with self-attention, it would look like this. So this is even a more zoomed in version of encoder, right? From this. So like it shows you, okay, so this is layer normalization. What does add and normalize mean? Just like you, it's just layer normalization. Let me see if I can find layer normalization here. No, okay. But that's what it is. Okay, this is kind of the full picture. Okay, of one encoder layer. Okay, just one encoder layer. It's already somewhat complex. This but we have 6, right? In the paper we have 6 of these. Okay, each goes through each other. This goes for the sublayers of decoder as well. Okay, so and this is the full architecture, and this corresponds to this picture in the paper. Okay, and we'll talk about the paper in a little bit if we have enough time. But this corresponds to that.
Sorry,
okay?
just one more question. So, and we always have like, or in the architecture, it's 2 feed forwards per encoder as opposed to a feed forward corresponding to each input word.
Well, I think this is only because we have 2 words here.
Yeah.
And this, I think this is just
we always have 2, and regardless of how many words.
Is that
No, I
true?
think there's one. No, I think there's one for each word.
One for each word. Yes, that's what I thought. Because we have 2 words, that's why you have 2 here.
Yeah. Okay.
Yeah.
Okay.
Yeah.
Thank you.
Yeah. Yeah. Sometimes it could be confusing because we're oversimplifying just with 2 words, right? So.
Oh
So
yeah,
is
of
it the
course, because we're making everything parallel, right? So it has to be per word.
The feed-forward networks don't have to do with the number of words, right? The feed-forward networks have to do with how within your encoder you've sliced, so it'll be 8 or whatever the chunking that you do. That doesn't have to do with the number of words. Here at the bottom, you're just feeding 2 words in this example. The number of feed-forward networks within an encoder has to do with how you chunk, not with the number of words. So don't get confused by the numbers being correlated to, in this case, as Wencheng just said, it's just a simplified picture. Within the encoder, the feed-forward network, how many they are depend on, like in the example he went through, it was, I think, chunked, meaning whatever slices you concatenate, that many feed-forward you will have. So I think in this case, 8. And that 8 has nothing to do with number of words that you send in. It has to do with how much concatenation you need to do.
Anyone else? Because if you already concatenated, why do you need to do 8 feed for? I mean, if we have 8, you're saying if we have 8 heads, we have 8 feed forward neural networks.
Yeah, I guess that's what you're saying, isn't it? Because you said the number of chunks, and the number of chunks is the number of attention heads.
Right, and then you put them through the feed forwards, and each of the feed forward.
I thought this is already concatenated, and you then multiply with this, then you get 1 output, not 8 outputs, and then you send it, and it says right here, then you send this to the feed-forward neural network. So I don't understand.
Okay, so that's the end feed-forward network.
Yeah. So and again, this is just 1 word, right? So I think it's 1 word per feed-forward neural network. I think that's what Joseph said, and that's what I thought as well.
I think when we look at the code, we'll be able to make sense of it. So
Yeah,
let's leave that
we will.
later.
Sure. Okay. So that's encoder architecture, and that's decoder. And notice this was right. We're taking the outputs of that and feed it into here, but we're not taking everything. We're taking just the K and V vectors and not everything. So and the query vector actually comes from itself. So your second decoder's query vector comes from the first decoder's query vector. That's how they're architected. And you have a linear layer in the end and softmax, then you have your output. Okay, so I want to bring attention to that. So BERT actually is all this, just this, and nothing like this. So there's no decoders in BERT, and just encoders, and GPT only has this decoders, and BERT has 12 of these encoders. I don't know how many decoders GPT has, but it's all decoders. GPT doesn't have encoders. So basically what I want to say is when we come to later evolutions or developments of transformers, we're not using all parts of transformers. Different architectures, neural network architectures are taking parts of transformers and run with it. So I want to just raise that here. Okay, the decoder side. Now we've covered most of the concepts on the encoder side. Decoder is similar, but not exactly the same. So yes, we're taking the K and V, right? So the encoder starts by processing the input sequence. The output of the top encoder is then the output of top encoder is then transformed into a set of attention vectors K and V. These are to be used by each decoder. Okay, so this graph is probably right. I don't know why this was graphed. So this was probably either inconsistent or yeah. But it literally says right here, only the top encoder, which is probably the last encoder, is then transformed into the set of attention vectors K and V. And then they're used by each decoder, right? So that hence the 2 different errors to each decoder, right? This decoder 2, this decoder 1. So each decoder, okay, in its encoder-decoder attention layer, in this layer, okay, so decoder 2 has this layer too. So these K and V only flow into this layer and this layer in the decoder 2, not this layer, not this layer, and not that layer either. So, which helps the decoder focus on appropriate places in the input sequence. Okay, so we're only taking the K and V right here. So after finishing the encoding phase, we begin the decoding phase. Each step in the decoding phase outputs an element from the output sequence. Okay. The following steps repeats the process until a special symbol is reached, indicating the transformer decoder has completed its output. The output of each step is fed to the bottom decoder in the next time step, and the decoders bubble up their decoding results just like the encoders did. And just like what we did with encoder inputs, we embed the add positional encoding to those decoder inputs to indicate the position of each word. Okay, so decoder also has position encoding, right? And let's just take a look at this graph a little bit because it's actually moving. Decoding time step 2, and you have M time 3 goes through that and outputs a decoding time step 4, outputs that student 5, student decoder, end of sentence. Okay, then you stop. Okay, so decoder goes through each time step, each word. Okay. So self-attention layer in the decoder operates in a slightly different way than the other one in the encoder. As we said, there's some differences. It's not exactly the same. In the decoder, the self-attention layer is only allowed to attend to earlier position in the output sequence. This is done by masking future positions before the softmax step in the self-attention calculation. The encoder-decoder attention layer works just like multi-headed self-attention, except it creates its query matrix. Remember I said query matrix was from the layer below it and takes the key and value matrix, K and V, from the encoder. So the query is from the decoder stack itself. The K and V are from the encoder stack. And that's what encoder-decoder attention is. And that's how it's different from just a self-attention layer. Okay, final linear and softmax layer. That's pretty straightforward. We're just doing linear layers, simple fully connected neural network, and that projects the vector produced by this stack of decoders into a much larger vector called a logits vector. So that's the logits vector passing through a linear layer, which is just a linear transformation, Wx plus b. Let's assume that our model knows 10,000 unique English words that it learns from its training data sets. This would make the largest vector 10,000 cells, right? Each cell corresponds to the score of a unique word. This is how we interpret the output of the model. I guess that, this is standard practice for many NLP models. Softmax layer that turns these scores into probabilities, just normalize that to 1. The cell with the highest probability is chosen. So in this case, it's M, so I am, right? So, and the word associated with it is produced as the output of the time step. So if your previous step is I, then you output M right here as number 5, because that's the highest probability. Okay, a little bit on the training, then we'll be done. So just a couple more minutes. Sorry, I'm dragging this along. Now that we've covered the entire forward pass process, let's talk a little bit about the intuition of the training. This is the index, is output vocabulary. Since we're training on a labeled training set, we can compare its output with the actual correct output. And you just, okay, so you have a 1-hot encoding of the word M. That's, I guess that's the target. Okay, loss function. So yes, so you literally just I guess doing cross entropy with these two vectors, right? It's the same thing as image classification, right? So doing cross entropy, and that's pretty straightforward. Cross entropy or chaos divergence. And okay, so no, this is oversimplified example. Each probability distribution is represented by a vector width equals to vocabulary size, and 6 in our target example, but more like 30,000 to 50,000. So we have a vector of this like 50,000, 30,000 to 50,000 as a length. The first probability distribution has the highest probability at the cell associated with the word I. Second probability distribution has the highest probability at the cell associated with word M. So hence I am. And so on until the 5th output distribution indicates end of sentence symbol. So I am a student, end of, that's the target model outputs, right? End of sentence token. After training the model for enough time, we would hope the produced probability distribution will look like this. So I still, you know, you wanted these to be highest. I am a student, end of sequence. Then again, like you do cross entropy, right? And because model produces outputs one at a time, we can assume that the model is selecting a word with the highest probability from that probability distribution, throwing away the rest. That's one way to do it. Another way to do it will be hold on to, say, the top 2 words. Then in the next step, run the model twice. Once assuming the first output position was the word I. And another time, okay, this is just a different way of handling the outputs. And that's it. 1242. And I want to pause here. I mean, does anyone have any questions? We probably don't have time to go through the paper now. I mean, unless you guys want to go all the way till like 1 o'clock, or we could leave this, you know, next time, and we can talk about a little bit about the paper. And please, if you can read it ahead of time, that'd be great. It will save us some time. We won't read through everything. We'll probably go through it till, I would say, like, you know, reading some important parts till like page 8, till the results. And we'll try to compare like this graph with what we have done here. And also, you know, talking a little bit about the mathematics, which we've already gone through. And how this, you know, the concatenation, remember, like concatenating all the heads together, you know, it's represented here with mathematics. And feed-forward neural network, how that's done mathematically.
Sorry, Ventek, when you are on that particular, so there are 2, I was wrong, you and Joseph were right. There are 2 feed-forward. One is the thing done after the chunk, and then there's also the position-wise feed-forward, in which case it corresponds to the number of words. So those are 2 different feed-forwards.
Yeah, and I guess it says right here as well, which is applied to each position separately and identically. So yes, so it's probably applied to each word separately. So, and we're going to talk a little bit about computation complexity, why this is so good, right? Why this can be, why didn't we just use that for BERT, or, you know, to train a size like BERT or GPT, because it was probably not as feasible. But like, look at this, O1 ON squared times D. It's faster and it's parallelized. It's allowing parallelization. So we're going to talk about this and some optimization training, how they set this up next time. And obviously we're going to try to see if we can, you know, go through this. This will take a lot of time as well, and we'll go through some implementation details next session. But please, you know, if you have time, read through the paper, read through like first 4 or 5 pages at least, and perhaps till here 4 or 5 pages ahead of time, then, you know, then you have a better understanding of what's going on. Cool.
Hey, Wenchang, you did a brilliant job. Thank you very much.
Thank you. Appreciate it.
Yeah, thanks, Wenchang. So we're going to push forward the schedule, the schedule for our Saturday classes to accommodate this the extra session that Wenchang has planned for attention and transformers.
Okay, great. So yes, and I love to quote Richard Feynman's what Richard Feynman said. What I cannot create, I do not understand, and that's why I really want to go through this. to actually let's at least go through the creation of the of transformer. So then we have a deeper understanding of how some of the details are implemented by code. So okay, on that note, thank you everyone.